going to circle back to a concept that we investigated earlier in the beginning of Chapter 5 with regard to differential equations, but it's going to be sort of geared toward a focus on how you might see problems on the AP exam. So the idea with the differential equation is that you're given information about the derivative of some function, and oftentimes you're asked to find what the original function was. The most common of these, most basic types, are what we call initial value problems, where we have the derivative of some function. We know the derivative is the cube root of x, and we know that there's a condition that the y value when x equals 1 needs to be 2. So the way we go about these is we set up the basic statement that the derivative of y with respect to x is the cube root of x, which I'll write as x to the 1/3. And now the critical step in these problems is to separate the variables so that you have your x terms with your dx and your dy terms with your y's. And we do that most often by like cross multiplying. So you can imagine taking this dx down here and multiplying both sides by dx to bring it up. We did this earlier in the year also when we looked at differentials. So we have this expression now, and essentially all we need to do is integrate both sides. So we can certainly rewrite this dy equals x to the 1/3 dx, but I'm just going to show that we're going to basically integrate both sides. And on the left side, the integral of dy is simply y, and on the right side, we're going to use just the power rule in reverse. So we're going to get x to the 4/3 divided by 4/3, which is like being multiplied by 3/4. And then we need to deal with our constant of integration. Now you might think we've done two integrations. We did an integration on the left side, we did an integration on the right side, so maybe we need a plus c on the left and a plus c on the right. But I think you realize that if you have two constants, one on the left side of the equation and one on the right side of the equation, for example, let's say you had x plus 2 equals 5, there's a constant, there's a constant. Well, that's the same as subtracting 2 from both sides and getting x equals 3, having a constant just on one side. So we're going to just add our constant of integration to the right side. And it's at this point that I always like to immediately solve for the constant. So we know that when x is 1, y is 2, so we can substitute 2 in for y and 3/4 of 1 to the 4/3. 1's going in for the x, and of course 3/4 times 1 to the 4/3 is just 3/4 times 1, which is 3/4. So we get 2 equals 3/4 plus c. So of course that means that c is 2 minus 3/4, which is 8/4 minus 3/4, which is 5/4. So we could write the equation y equals, right here, this is what we're using, 3/4 x to the 4/3 plus c, but now that we know c is 5/4, we can just put that in there, and that is our solution. So if we wanted to check our work, what we can do is make sure that when you plug in 1, that you get a y value of 2, and I think you can see that pretty quickly. And also, if you were to take the derivative of this function, you should get back to this guy here. And if both of those conditions are met, you know you got the problem right. So we're going to move on to our next example here, where we have a little trig going on. But again, we're going to start with the same idea that we need to separate the variables. We need to put the dt over on the right side with the t's. So we're going to say dy is equal to secant squared of t minus sine of t dt. And then we're just going to integrate both sides. And of course, integrating dy is y. And integrating secant squared, that integrates up to tangent. And negative sine integrates up to cosine, because remember the cosine derivative is negative sine. And then we'll put our plus c on this side. And now we use our condition that at pi over 4, we need to have a y value of 1. So I'm going to put a 1 here and a pi over 4 in for each value of t. Cosine of pi over 4 plus c. And then we can evaluate each of these. The tangent of pi over 4 is 1. The cosine of pi over 4 is root 2 over 2. And that's got to be true. So if we subtract 1 from both sides, they're going to go away, and we're going to get negative root 2 over 2 is going to be equal to c. And so we could use that back here in this original equation that we got and say y is the tangent of t plus the cosine of t minus root 2 over 2. And that is, again, if we wanted to check that solution, if you take the derivative of this, you should get back to this. And if you plug in pi over 4 for the t's, you should get 1 for your y value. I can maybe leave that to you. Now, another type of these problems are simply stated as verbal models, and sometimes we're asked in a multiple choice scenario to match which equation would match up with this. Now, I've altered this question slightly just to have you write a differential equation to turn it into like more of a free response question. Now, the first thing that you're going to recognize, or you should recognize, is when they say something is directly proportional. For example, if y is directly proportional to x, that's something that you talk about in Algebra 1. That's equivalent to the statement y equals kx, which basically means as x gets bigger, y gets bigger, and when x is 0, y is 0. So that's kind of a magic formula to know that if two quantities are directly proportional to each other, that means one is equal to k times the other one, where k is some constant. And a lot of times in these problems, they'll give you enough information to figure out what k is, or they might even just tell you what k is. But in this first example, we're just going to use k because they're telling us rather that the rate of change of the volume of water in a tank with respect to time. So what you need to recognize is rate of change of volume with respect to time. We have a way to write that in calculus, and it's dv dt, just like when we were doing our related rates problems. And it says that is directly proportional. Okay, so that's going to be equal to k times the square root of the volume. So the square root of our volume. And this would be the differential equation that describes that scenario. Now, that's all we're being asked to do in this problem, so we could circle that as our answer and move on. If we had information about the volume at a particular time, we would proceed as we did in the first couple of examples where we'd separate the values, bring the v's down here and the t's up here. I guess I should probably show you doing that. It would be dv over the root of v would be equal to k dt, and I got that just by cross multiplying, bringing the dt up here and putting the root v in the bottom. And of course, both of these, you could certainly integrate that, and you would have some integral expression, and then you could integrate that with a plus c, and if we had an initial condition, we can move on from there. Don't worry, we're going to get plenty of practice with that. So now in this next example, just a little multiple choice sample here. And they say P of t is the size of a population at time t. Which of the following differential equations describes linear growth? So if we're talking about a function that has linear growth, that means that the function must satisfy like y equals mx plus b, but mainly that the growth rate would be constant. That's the big thing we know about lines, is that their slope is constant. So if you look at these choices here, the only one that indicates that the rate of growth is constant is this one right here. dp dt is 200. That's literally saying the rate at which the population is changing over time is 200. It's always 200. It doesn't matter what the time is. All of these other ones depend on either time or what the population is itself. Both of those are certainly valid situations that could come up in the real world. They're just not what's being described in this problem. So we would just choose answer A because it has a constant rate of growth, and we'd be able to move on from there. The sucker answer there, I think, would be this guy, because people see 200t as think of that as a linear function. But remember, we're talking about the rate of change being constant. If you were to integrate this guy, you'd get a quadratic. Okay, so I had a bit of a flake out, and I actually copied example 3 down here in example 5. It's the same exact problem, but don't worry about this. We're going to get, like I said, we're going to get plenty of examples where we have to come up with a model and then maybe eventually solve those differential equations. Now, for example 6, we've seen a couple of these in our problems of the week throughout the year. And it says, which of the following is the solution to the differential equation y double prime minus 4y equals 0? And I wish I had a magic wand that I could wave on these problems for you to just tell you this is exactly how you do them. But essentially, these are very typically, well, almost always multiple choice types. And what you kind of have to do is just look at each problem and look at each example and decide whether it fits it or not. Now, this is a multiple choice question where only one answer, is going to be the right answer. It's not like you're going to pick 2 or 3 of these that actually all satisfy this. But here we go. So they're talking about y double prime. So for all of these equations, we're going to need the second derivative. So e to the 2x, the first derivative is e to the 2x times 2, which we would write as 2 e to the 2x. And then the second derivative would be 2e to the 2x times 2, which is going to be 4e to the 2x. Now that looks like a pretty good candidate for a victory here, because if we plug in y double prime, which is 4e to the 2x, and we subtract 4 times the y function, which is just e to the 2x, do we get 0? Yes, we do. So that's our answer, and we could just move on. Now, what might be a good exercise as review for your students doing this is check and see, all of these sort of are good guesses. They're not questions that would be like right way out of the realm of possibility for being correct. So you should probably take your time and find the second derivative of choice B and see if it works. I'll tell you it's not going to, but maybe you can see why, and similarly with C and D. Now, example 7 is reminiscent of a portion of a free response question from a few years ago. I think it was around 2017. They had one as part of a free response problem here that was similar to this. Now, frequently when we get these differential equations like we do here, more times than not, way more times than not, what you'll be able to do is get your x's on one side and your x's and dx's on one side and your y's and dy's on the other side. And that's referred to as separation of variables, which we're going to talk a lot about. This is not one of those cases, though. But they want you to find the values of m and b so that this thing is a solution. Y equals mx plus b is a solution to this differential equation. So you're like, oh my goodness, this seems awfully abstract. But if you think about y equals mx plus b, of course, we know that's a linear equation. And the slope of this function is given by m. So in other words, dy dx is simply m. So what we're going to do is just be kind of crafty, and I'm going to rewrite this equation that we were given, dy dx is equal to 1/2 of x plus y minus 1. Now all I'm going to do is, because we know that this has to be true, that the derivative has to be equal to m, and that y right here is given as mx plus b, I'm just going to substitute those and we'll see what happens here. And I'm just going to trust that we're going to be able to work this out. So on the left side, dy dx turns out to be m, and we have 1/2 of x plus y, but remember y is mx plus b. So I'm going to put in mx plus b, and that's that, and then we have a minus 1 at the end. So what I see here is a situation where this stuff, the stuff on the left has to be equal to the stuff on the right. So when I look at those first 2 terms that I underlined there, I see they have a common factor of x. So if we took the x out and we had 1/2 plus m and then b minus 1. So here's the thing. X is our variable, right? That's changing. It's what you're plugging in numbers for. This left side has no x's in it. So that means the right side should have no x's in it. And the only way that this quantity of x's is going to turn out to be 0 is if 1/2 plus m turns out to be 0. And of course that means m equals negative 1/2. Now that's a huge jump that I think most students wouldn't be willing to take. But it does make sense if you think about it. On this side there's no x's, on this side there's this many x's. So in order for them to be equal, this quantity has to be 0. I refer to this as equating coefficients. The coefficient of x on the left side is 0 because there's no x's here, and the coefficient of x on the right side is 1/2 plus m. Now that we know that, that means the constants on the left, which is m, has to be equal to b minus 1. So now we can combine that fact that m has to equal b minus 1, and then use the fact that m is negative 1/2. Then we can solve for b. And we get b equals positive 1/2 by adding 1 to the other side. So the answer to this problem is m would be negative 1/2 and b would be positive 1/2. that is a tricky question, but like I said, they asked one like that as part of a free response. I think it was back in around 2017. All right, in this note sheet, we've got about three or four more problems, I think, and essentially they're all come down to the same problem type, where they give you a differential equation, they ask you to solve it given a particular initial condition. These are really, really, really common on the free response portion, so we want to get good at this, and virtually every single one of these, not virtually, but all of these are going to have this idea about separation of variables. So I'm going to get you through a couple of these, and you're going to get some practice on this. So here we go. The first one, we want to have y's and dy's on one side and x's and dx's on the other. So with this equation that we have dy over dx is equal to negative 2xy, I want to bring these dx's up and this y down here, which is going to give us dy over y is equal to negative 2x dx. And now we're in business because both sides of that are fairly straightforward integrations. So that's what we're going to do. We're going to integrate the left and we're going to integrate the right. You should recognize the left side as integrating up to the ln of the absolute value of y. And on the right side, we're going to get negative 2x squared over 2 plus c, and realize that these 2's are going to kill each other. So we have the ln of the absolute value of y is equal to negative x squared plus c. Now, it's at this stage, you'll see different teachers will take a different approach to this. I really like to solve for the constant right now. As soon as you've done the integration, go ahead and plug in x equals 1 and y equals 4, and we'll be able to solve for c. So in doing so, we get the ln of 4. Now, we don't really need those absolute values because 4 is a positive number. But that's equal to the opposite of 1 squared plus c. And of course, the opposite of 1 squared is just negative 1. So if we add that over to the other side, we get the ln of 4 plus 1 is equal to c. So we now can use that up here and write our equation as the ln of y is equal to negative x squared, or the opposite of x squared, plus the ln of 4 plus 1. I think I'm going to write that as negative x squared plus 1 plus the ln of 4, and you'll see why in a little bit. So there's our equation, and you're like, wait a minute, that's not done. And you're right, it's not done because we don't have y by itself. We have the ln of y. So what you have to remember is ln of y is equivalent to log base e of y. And if that's equal to something, that means e to that something is equal to y. Remember, the base raised to the answer equals what you're taking the log of. So e raised up to this quantity, negative x squared plus 1 plus the ln of 4, is equal to y. And AP is not real big on simplification, but I kind of am. I think you should be able to recognize these situations. You could sort of think of this quantity as e to the negative x squared being multiplied by e to the first being multiplied by e to the ln of 4. Because remember, when you multiply like bases, you add the exponents. Now, neither of these are very interesting, but this one is, because e to the ln of 4 is just 4. So I would rewrite that as 4e to the negative x squared plus 1. And that's my solution. Now, again, a little bit tough to check these, but if you took that derivative and tried to use this expression, it'd be a little tricky because you'd have to plug this expression back into your answer, but it should work. And again, what definitely works is that when x equals 1, your y value would be 4. That's easy to check. Okay, we're going to move on to our next example here, example 9. Again, we have another pretty straightforward differential equation. The first step is going to be to separate the variables. I'm going to bring the y squareds down below and get dy over y squared is equal to 5 dx. And again, bring the dx's up to the other side. So that's standard operating procedure to get started on these problems, to separate the variables. Now, we have to integrate both sides. So I'm going to integrate this, and we're going to say that the left side is the integral of y to the negative 2 dy, and that's the integral of 5 dx. And remember, quite a few students might look at this and start to think about ln, but remember, you're only going to get an ln resulting from dy over y, not dy over y to raise to any power other than 1. So now we're going to just use the power rule in reverse. So we're going to get y to the -1 over -1. And on the right side, 5 dx integrates to 5x. Put a plus c there. And I want us to use our initial condition right now, but I think I want to clean up this left side. Because remember, y to the -1 means 1 over y. And then we have this negative sign here, so I think I'm going to write that like that. And I think that's probably the cleanest way to write that. So there's our, like a rough version of our solution. And now we're going to use the fact that when x is 0, y is 3. So we're going to come up here and say, okay, well, if y is 3, that becomes -1 over y becomes -1 over 3. And that's equal to 5 times 0 plus c. So that tells us that our constant is -1/3. So now you come back to our equation, and we have -1 over y is equal to 5x plus c, but c is -1/3. Now, here's the thing. You have to get a solution for y, and we don't have a solution for y yet. What we have a solution for is -1 over y. And unfortunately, when you have a sum or a difference over here on the right side, it's not so easy just to reciprocate both sides. What we need to do is express this as one fraction, and then we can reciprocate both sides. So in other words, if you have 1 over 6 is equal to 2 over x, it's fine to reciprocate both sides and say 6 over 1 is equal to x over 2. That's what we want to do. We want to use that idea. But we have to have a single fraction on each side. So what I'm going to do is I'm going to get a common denom here on the right side, and basically take this guy and multiply it by 3 over 3. And so that gives us -1 over y is equal to 15x over 3 minus 1 over 3. So -1 over y is equal to 15x minus 1 over 3. Now we can take that and simply reciprocate both sides and get -y is equal to 3 over 15x minus 1. And we want to get y isolated, so we could divide both sides by -1. And I think I would do that by recognizing that 15 minus 1, when you reverse that, you get its opposite, 1 minus 15x. So I would probably just write it as 3 over 1 minus 15x. So basically, I just multiplied both sides by -1. So that would be my solution for that guy. And again, if you felt like it, you could take the derivative of that thing and see if you get back to this relationship. But that's usually not trivial to do that. It's much easier just to make sure that at least you get the initial condition set, that when x is 0, y is 3. And I think you can see that's definitely going to work. All right, let's move on to the next one. So looks like a somewhat more complicated equation here, but again, we have that case where we can separate our variables fairly simply. We can bring the y down on the left, so we're going to get dy over y, x over y, and that's going to be equal to bringing that x up here and getting 2x dx over x squared plus 1. And this is where we thank our integration skills, and working so long on those different complicated integrations we did. Hopefully we can recognize that on the right side, what we have is a classic u-sub problem. So we need to integrate the left, we need to integrate the right. The left side, of course, is just going to be the ln of the absolute value of y. And on the right side, hopefully you can see that if you let u equal x squared plus 1, then du is simply 2x dx. And of course, we have that right up there. So this will be the integral of du over u. And so integrating that, we're going to proceed and get the ln of the absolute value of y is equal to the ln of the absolute value of u plus c. But let's come back to what u was. Ln of y is equal to the ln of x squared plus 1 plus c. And this is a great time to use our initial condition. So notice that both of our values are such that that the absolute value is not going to be an issue because they're giving us positive values. So we can just say the ln of 1, putting the y value in there, is equal to the ln of 0 squared plus 1 plus c. Of course, this is 0, and this is 0 plus c, so our constant is 0. So what we have is coming back to this version of the equation, we had ln of y is equal to the ln of u, I guess we're using this one down here, which was x squared plus 1. Now I'm just going to put those in parentheses. Again, we don't need the absolute values because our quantities are strictly positive. So what we want to do now is essentially recognize that we can, exponentiate both sides and get y equals x squared plus 1. In other words, if you have the ln of a equals the ln of b, the only way that's going to happen is if a equals b. As we wrap up this example, this batch of problems with this example 11, it might be a good idea for you to take a look at this one stated as we've got the differential equation dy dx is 3x squared plus 1 all over 2y with the initial condition f of 1 equals 4. And just kind of try this one on your own. So pause the video, go off on your own, and see if you can separate the variables, integrate both sides, solve for the constant, and then solve for y. That's kind of the process that we go through here. Again, separate the variables, get y's with dy's, x's with dx's, integrate both sides, and as soon as you're finished integrating, that's the best time to use the initial condition to solve for the constant. And then once you have that constant solved for, you can put it back into the original equation that you right after you integrated, and then try to get y by itself. So try that, pausing the video, and then you can come back and check the work and see if you got it right. So here we go. We're going to have 2y dy is equal to 3x squared plus 1 dx, and integrating both sides we get y squared on the left, and on the right side we get 3x cubed over 3, which is x cubed, plus an x with a plus c. And at this point we use the condition that when y is 4, that would be 4 squared, we need to get 1 cubed plus 1 plus c. So it looks like 16 equals 2 plus c, so our constant is 14. And now if we put that right in there, we can say y squared equals x cubed plus x plus 14. And that would be great if they were asking us to solve for y squared, but they're actually asking us to solve for y, so we got to take square roots of both sides. Now, when we do that, you got to be careful, going back to your Algebra 1 knowledge, when you take square roots of both sides, you got to acknowledge that there's a positive and negative root. So we get x cubed plus x plus 14, but it's inappropriate to leave this ambiguity as far as whether we're going to take the positive root or the negative root. And so the way you always solve that question is take a look at the initial condition. And the initial condition that we have is when x is 1, y needs to be 4. So that means we need to choose the positive root of this guy. So our final answer would be y equals the positive root of x cubed plus x plus 14. Again, what I did there is I said, okay, well, if we plug numbers in, is this true or not? When I plug the 1 in for the x's and the 4 in for the y's. This is a true statement. Had I chosen the negative root, it would not be a true statement. This is not true. 4 does not equal negative 4, so I had to choose the positive root. So there we go. So hopefully you got that, and that's a good thing. Every few years that comes up as a free response question where you need to choose which branch of that curve is the correct one, but it always comes from this initial condition. Had it been, f of 1 equals negative 4, then we would have chosen the negative branch of that square root function. So there you go. It's a great collection of problems that are comparable to what you could see on the AP test.